Welcome one and all. In this today's video, we'll discuss about the concept of self-orthogonal. So, which is nothing but the continuation of the previous lecture, orthogonal trajectories. So, in the orthogonal trajectories, we have one more concept known as self-orthogonality. So, self-orthogonality means a family of given curves is said to be self-orthogonal if its orthogonal trajectory is same as itself, means whatever may be the given family, if its orthogonal trajectory is same as itself, then we can call that given family as self-orthogonal. Okay, so how we can identify such type of problems or such type of families, now we will see with the help of one problem. So show that the family of confocal conics given by x square by a square plus lambda plus y square by b square plus lambda is equal to 1 is self-orthogonal. So here one family of confocal conics is given and it is nothing but x square by a square plus lambda plus y square by b square plus lambda is equal to 1 is self-orthogonal. So this is what we have to prove now. Now let us see. So first of all we have to find out the orthogonal trajectory of this family. Okay, now we will see the solution. So as we have discussed in the previous video, so we will try to find this one, find the orthogonal trajectory of this family also in different steps. Okay, so first of all we will write the given family. The given family is, what is that? X square by a square plus lambda plus y square by b square plus lambda is equal to 1. So here we have to observe that lambda is the arbitrary constant. Here we have to observe that lambda is the arbitrary constant and a and b are only constants. So means here we have only one arbitrary constant. So as we have discussed earlier, so we will solve this as in the different steps. So first one, step 1. In step 1 what we have to do? So we have to form the differential equation of the given family. Okay, means of equation 1 simply. So as here we know that we have only one arbitrary constant, so therefore we have to differentiate this equation 1 to eliminate that arbitrary constant lambda. So now for that, now you differentiate equation 1, simply I am writing like this, with respect to x on both sides, then we get derivative of x square is 2x, 2x by a square plus lambda plus derivative of y square is 2y into y dash. I am writing, instead of writing dy by dx, here I am writing y dash divided by b square plus lambda is equal to, the derivative of 1 is 0 because 1 is a constant. Okay, now we can cancel out that 2 and if you take the LCM and simplify, I can write it as otherwise. Okay, I will write it once again. So by cancel out 2 we will get x by a square plus lambda plus y dash divided by b square plus lambda is equal to 0, implies you can write. So that implies, now you take the LCM, a square plus lambda into b square plus lambda is the LCM, then we will get x into b square plus lambda plus y dash into a square plus lambda is equal to 0. Okay, now we have to find the value of lambda. So that implies lambda is equal to, so what are the terms here we have? So b square x here we have and a square y dash we have, so those terms will go to the right side. So means we can write minus of a square into y dash plus b square x divided by, what are the coefficient of lambda? If you take lambda as common, x plus y dash, so that comes in the denominator, x plus y dash. So this is the value of lambda. Now what we have to do? We have to eliminate lambda from the equation 1. So therefore now we substitute the value of lambda in equation 1. So therefore you write, therefore by substituting equation 2 in equation 1, so we get what we get, x square divided by a square plus lambda we have. What is lambda? Lambda is equal to minus of a square y dash plus b square x divided by x plus y dash. Better what I will do is I will write in the next page. Substituting 2 in 1. Okay, now we will substitute this value of this lambda in equation 1. In the next page I will write so that it may be clear for you. So x square by a square plus lambda we have. So x square by a square plus lambda. Lambda means minus of a square y dash plus b square x divided by x plus y dash. Let me check whether it is right or wrong. So value of lambda is a square y dash plus b square x. A square y dash a square y dash plus b square x divided by x plus y dash plus y square divided by b square plus lambda, means b square plus lambda means again minus of a square y dash plus b square x divided by x plus y dash is equal to 1. So this is the equation after replacing lambda value in the given equation. Now you just simplify. So here in the denominator x plus y dash is the LCM, that therefore we can write it as x square into x plus y dash whole divided by, okay, now what is LCM? X plus y dash is the LCM, means we will get a square into x plus a square into y dash minus, here you write it, minus of a square y dash plus into minus b square x. Okay, so similarly here also plus, here also in the denominator x plus y dash is the LCM, so therefore it goes to the numerator. So y square into x plus y dash divided by, so b square into x plus y dash, in the sense b square x plus b square y dash minus of a square y dash minus b square x is equal to 1. Now I just simplify this here, a square, so this is y dash, sorry, so a square y dash and a square y dash will cancel out, and here minus b square x plus b square x cancels out. So what else remains? This implies x square into x plus y dash divided by, here what we have, a square x minus b square x. If you take x as common, then we can write it as a square minus b square. Okay, similarly here also in the second term, y square into x plus y dash. So in the denominator, if you observe, b square x cancels out, and we have b square minus a square of y dash. So now you take y dash as common, then we'll get b square minus a square. So otherwise you, okay, one step we may write it. So what we have, if we take y dash as common, then we will get b square minus a square. So y dash into b square minus a square is equal to 1. Okay, now if we observe this, we can cancel out this x in square here, and here also y in this square. Then what remains? So, and if you observe here, in both the terms the denominators are same. Here a square minus b square here we have, and here also by taking negative as common we will get a square minus b square here we will have. So therefore here I can write a minus here. Both total we can take a square minus b square as common. Then we can write 1 by a square minus b square into. So here if you observe what we have in the numerator, x into x plus y dash, x into x plus y dash we have, and here already we took minus as common, that's why minus of y into x plus y dash. So actually here that x plus y dash also we can take it as common, but of course we may write it in the next step. So now here in the numerator we can take x plus y dash as common. Okay, so then we get, if you take x plus y dash as common in the numerator, what is left over? So here we have x minus, sorry, here by y dash we have, then we get x minus y by y dash here we have is equal to, now you take it that a square minus y square b square, you can write it here a square minus b square. So now the lambda is eliminated here. Now this is nothing but the differential equation of the given family, which is the differential equation of the given family 1. So now what we have to do in step 2? So in step 2 what we have to do? We have to replace dy by dx with minus dx by dy. In the sense we have to replace y dash with minus 1 by y dash. So now what we have to do? Just I am writing here the same, replace y dash by minus 1 by y dash in equation 3. Okay, so then what we will get? So in place of y dash, so x plus y into, in place of y dash we have to write minus 1 by y dash. This is the first term, and coming to the second term, x minus 1 by y dash. So in place of minus 1 by y dash directly we can write y dash. So once again, in place of minus 1 by y dash, so minus 1 by y dash can be replaced with y dash. So therefore you can write x plus y dash is equal to a square minus b square. Now here what we have, this implies it is nothing but x minus y by y dash into x plus y dash is equal to a square minus b square. Okay, so therefore which is nothing but the differential equation of the orthogonal trajectory. Okay, so you just can write it. So which is the differential equation of the orthogonal trajectory of equation 1. Now but if you observe the equations 3 and 4, equation 3 is the differential equation of the given family, and equation 4 is the differential equation of the orthogonal trajectory. Both are nothing but same. If you observe, the equation 3 and 4 are same. So in the sense, once again if we solve this equation 4, again we will get the given family only. So that's why no need to go for step 3 here. So this is the advantage in the evaluating the self orthogonals. Okay, so if you can identify that equations 3 and 4 means the differential equation of the given family and the differential equation of the orthogonal family, orthogonal trajectory, both are same, means the given family is self orthogonal. Why? Because if we solve this equation 4, once again we will get the given family only, because this equation 3 is nothing but obtained from the given family only. So therefore no need to solve this differential equation, as equations 3 and 4 are same. So now we can conclude that the given family is self orthogonal. So that's why here you write it so clearly. Clearly the equations 3 and 4 are same. Therefore the given family is self orthogonal. Okay, so this is how we can identify whether a given family is self orthogonal or not. So let me tell you once again. In step 1 we have to find out the orthogonal trajectory. In step 1 we have to form the differential equation of the given family. In step 2 we have to replace dy by dx with minus dx by dy in that obtained differential equation, and if you find that both the differential equations are same, then we can conclude that the given family is self orthogonal. So this is how we can identify whether a given family is self orthogonal or not. Thank you.